Hi, welcome to module 24. In module 23 we saw the basics of CMOS, and if you have seen the video, then you would notice that there are lots of electrical parameters that I talked about. So you need to have a very rough understanding of what these electrical parameters are, and that will be necessary for this video. So let us look at the notion of delays. So in this lecture we are going to look at delays. So I am going to take a basic device, so it could be NMOS or PMOS. So in this case, if I look at a NMOS device, I want to see what is the delay because of this. So first of all, it's a physical entity, right? We are going to look at a physical entity. It's not an abstract switch where I can talk about zeros and ones. Eventually it's an electrical circuit which I want to talk about. So there are two devices here, there is a PMOS device and a NMOS device. So there is a NMOS device here and there is a PMOS device here. I want to talk about how to equivalently transform them into electrical circuits, and this will be useful for delay calculation. What we are going to do is, we are going to assume that there is this NMOS device here, and I already mentioned in the previous video that there is a gate to various kinds of capacitances. There is gate to drain, gate to source, so different kinds of capacitances were there, right, and gate to substrate. Let us say I add all of them and I put them as one capacitance here. Right. So let us not worry about these quantities here. So G is gate, D and S are drain and source, and what I have is, if I have an inverter, then I am going to have a NMOS device, right. So I am taking one particular NMOS device. So in this NMOS device, I know that there are several capacitances from gate with respect to D, with respect to S and with respect to substrate. So since all these are capacitances in parallel, I could add all of them up and I will have that as one single capacitance here. Similarly, between the drain and substrate, I have some capacitance, right. I will have that as a capacitance here. Similarly, I have some capacitance between source and substrate and whatnot, I will have them here, right. So what we have is, we have three different capacitors, and I am also going to assume that this is an electrical circuit, right. So it has equivalent resistance, I am going to assume that there is a resistance. So what I am going to do is, I am going to take a transistor and I am going to treat it as though it is an ideal switch like here, plus some capacitances and resistances. So once I put an ideal switch here with this extra paraphernalia, all the capacitances and resistances, then I can forget that there is a switch there. So I will assume that the ideal switch has 0 delay. I will analyze the delay only in terms of all these capacitances and resistances outside. So otherwise we need to deal with the actual device every time. So instead I will assume that there is an ideal switch which has 0 delay, but all the delay in the transistor is actually exposed to us as though they are because of resistances and capacitances. So if I have a unit NMOS device, what that means is, if I have a NMOS device of width 1 unit in whatever technology you make, then let us assume that it has equivalent resistances, resistance R and some capacitance C. So after all, these are physical material, right. So physical material, if you put a metal or different kinds of material, you will have some resistance and capacitance because of that. So we will assume that unit NMOS has a resistance R and a capacitance C. Typically in most in older technologies, it used to be that unit PMOS device, if I take a PMOS device which has the same width as the NMOS device, its resistance is usually double. So there is a physical reason why it is so, but let us assume, let us take this for a fact now. A unit PMOS device usually has double the resistance, but has the same capacitance as though as it is for an NMOS device. So PMOS device has almost twice the resistance of a equivalent NMOS device if they are of the same size. So let us see how a NMOS device would look like. We took various gate capacitances, lumped them here, and we took various capacitances and put them here, and there is a resistance here. So resistance is usually inversely proportional to the width and capacitance is proportional to the width. again these are to the first order, it is correct. So, resistance is inversely proportional to the width. So, if I have a PMOS device of width k, then the unit resistance gets divided by k, but the capacitances all go up by a factor of k. So, if k equal to 1, then I have R here, C here, C here and C here, but if k is greater than 1, then the resistance goes down by that fraction and all the capacitances go up by that fraction. So, that is true for the PMOS device also. So, whenever, so if I have k equals 1, I have again equivalent gate capacitance which I have lumped at the gate terminal, I have some capacitance which I have lumped at the source terminal and some capacitance that I have lumped at the drain terminal. And in this case the capacitances are actually between VDD and the source terminal and VDD and the ground terminal and VDD and the gate terminal, unlike here where it is capacitance between the ground and the 3 terminals. And now if I put k equal to 1, I have 3 capacitors for the 3 terminals and one resistor which has an equivalent resistance of 2R. So, for a technology for equivalent NMOS you will have twice the resistance, right. However, if k is greater than 1, if I have a transistor that is wider, then what would happen is all the capacitances go up by that fraction and the resistance actually goes down by that fraction. And this is the basic setup behind a PMOS and a NMOS device. So, now if I give you a PMOS, if I give you a CMOS circuit, I can take the NMOS devices, put this network there, take the PMOS devices, put this network there and treat it as though it is an electrical circuit instead of a semiconductor circuit. And in electrical circuits we go and look at what is called the RC constant or the RC delay. The product of resistance and capacitance gives you the notion of a delay, because higher the resistance, larger the delay, larger the capacitance, larger the delay. So, R and C as a product gives you the overall delay. Let us take a basic inverter. So, the basic inverter is here. So, let us say I take this inverter and I have connected it to another inverter. So, Y is A bar and let us say Z is Y bar. So, Z is actually A. I have, so this is just to show you electrical parameters. So, this is not how to design a buffer, I am just showing you how to calculate various electrical parameters and so on. So, I have this PMOS device here. Instead of a PMOS device, I will put the equivalent circuit here. So, I have so what I have is I have a transistor of width 2 here for this PMOS and a transistor of width 2 here for this PMOS. So, this capacitance is 2C, this resistor is 2R by 2 which is R, and this capacitance is 2C also. This is a NMOS device. So, NMOS device of width 1 will have 2 capacitances of C and C respectively and one resistance R. And if I go and look at it from this gates perspective, this inverter is driving 2 gates, right. So, it is driving the gate terminals, it is driving the gate terminals of this device and this device, and at the gate terminal of this inverter. So, this inverter has 2 devices, one PMOS and one NMOS. So, this branch is seeing a capacitance of 2C and this branch is seeing a capacitance of C. So, the equivalent circuit as seen from this inverter's perspective is this setup. At this point we can assume that these resistances, so these 2 switches are ideal switches, right. Now, if I put A equals 1, then this switch, right, will act as a conducting switch and this switch is open or non-conducting. And if you go and look at the resistance, then this is a pull down network. If I put A equals 1, this Y will get pulled down, right. So, what you have is the equivalent electrical circuit for the pull down network. So, this capacitance and this resistance gets detached, you are not in charge for that. However, you have this capacitance, this 2C and C. So, what you have is you have this resistance and you have equivalent of 2C plus C plus 2C plus C or 6 equivalent capacitances. So, we have to discharge 6 equivalent capacitances through a resistor R, which means the delay of the circuit is 6 times RC. So, let me just quickly run you through what I did. I took 2 inverters. From this inverter's perspective, if I go and look at the delay, what it has is, this is the equivalent of the PMOS device, and this circuit is the equivalent of the NMOS device, and the capacitance that you are seeing because of the load from here is 2C and C here. Right? And if I put A equals to 1, then this device is cut off, however, this device is on. When this device is on, this capacitor does not have to discharge. So, it is already at 0, so this will be 0. You have this capacitor here and this 2C here, and this 2C and C are here. So, if you add all of that up, that is 6C. So, delay is 6 times RC for this inverter to pull down the output from 1 to 0. Similarly, if this transistor is closed and if this transistor is open, then you will have a 2C here, a 2C here, and you will have these 2 capacitances and this capacitance here. Right. So, equivalently you can go and derive the delay for it, and you will see that the delay is proportional to R and C. So, there is some constant involved here, it is proportional to R and C. So, this is the notion of a delay. So, if I have this delay equals 6 RC is what is called the high to low delay. If the output goes from 1 to 0, to do that I need delay of 6 units or 6 RC. Right. So, let us look at different parameters now related to timing. The first parameter we are going to call it rise time. Rise time is, if I give you a voltage waveform, then the time required for a signal to transition from 10% of its maximum value to 90% of its maximum value is called the rise time, and fall time is the time required from 90% of its maximum value to the 10% of its maximum value. So, generally the maximum voltage that we want to operate the device is at VDD. So, we are talking about 10% of VDD to 90% of VDD is the rise time, and fall time is 90% of the VDD to 10% of the VDD. And propagation delay is usually you measure from when the input crossed 50% of the input voltage to the time at which the output crosses the 50% value. So, let us see various parameters as we go along. So, let us look at this picture here. We have this blue waveform here, and this 0.5 times Vmax is here. So, if I measure the amount of time taken to go from 0 to VDD, right. So, that is usually the rising edge, right. This is the rising edge. Instead of measuring from 0 to VDD, we usually measure from 10% of VDD to 90% of VDD. That is usually called the rise time. And similarly, from 90% of VDD to 10% of VDD, we will call that the fall time. So, this signal is usually an ideal signal. However, you may have a waveform which is somewhat like this. So, this is what you may see in a real circuit. It may not even be a nice trapezoidal structure like this. You may see things which are slightly different. And the notion of TPLH or the propagation delay from low to high is, if I give this as the input waveform, right, the what is the time taken for the output to go from low to high, that is called TPLH, and TPHL is from 50% of the input to 50% of the output, whatever time it takes, that is called TPHL. So, this is just a circuit to illustrate various examples, and with these waveforms you can understand what rise time and fall times are and what TPLH and TPHL are. So, basically LH is low to high, HL is high to low, TR is rise time and TF is fall time. So, various ways in which you can measure the delay itself is possible, and when we have various gates, gates have different values for TPLH, TPHL, TR and TF. We need to be able to combine them and say that this is the delay of the circuit. So, eventually if I want to sell you a chip saying that, oh, this is my processor and it will run at 2 gigahertz, I want to tell you that this will be operating at 2 gigahertz, right. So which means every 0.5 nanoseconds you should be able to do an operation. You are not quite worried about whether it is rising from high to from low to high or going from high to low and so on. If I give you too many parameters, it is very confusing, but this is the underlying setup. The underlying setup is we have all these parameters. So let us look at how to analyze the combinational circuits for their delays. So for every gate I can associate something called TPLH and TPHL. So there is a certain time it will take to go from low to high, and there is a certain time that it will take to go from high to low. Typically TPLH is usually higher than TPHL. This is because of the asymmetry between NMOS devices, which will bring down the value from high to low, being better conductors than PMOS devices which can pull up. So pulling up takes more time usually than pulling down for circuits that are for transistors that are sized similarly. So let us assume that you have a circuit like this. So I give you a circuit V in and there is V out, and what I have done is I have taken V in, I have given it to an XOR gate, and I have given 3 inverters here and so on. If I do something called basic functional analysis is I want to derive V out in terms of V in as an equation, then V1 will be V in bar, V2 will be V in itself, V3 will be V in bar. So V out will be V in XOR V in bar. So anything XORed with its complement is 1, so V out will be 1. If I take this circuit and if I logically analyze it, V out should be the same as V in itself. However, all these inverters and this XOR gate have delays in them. They take a certain time, once an input appears, they take a certain time for the output to switch, and I want to characterize that. So let us see the delay of this circuit. So the circuit is given here and the delays are given here. So let us start with the waveforms. I will start with time t equal to 0, and let us say that there is a 0 to 1 transition at the input. So I know the high to low and low to high transition delays for each of these gates. I want to see what is the transition delay for the whole circuit. So if I give 0 to 1 transition at V in is directly connected to V1 and this XOR gate, right. So at a delay of 2 units, I can expect V1 to change from 0 to so V in is changing from 0 to 1, I can expect V1 to change from 1 to 0. So this 1 to 0, this is the high to low delay of the inverter, that is 2 nanoseconds. If you observe the output of output V out, V in is also driving V out, right. So the output is also going from high to low, let us assume. If it is going from high to low, then its delay is 4 nanoseconds. So you can see that this transition from 0 to 1 is causing V out from 1 to 0. So in steady state, V out would have been 1, right. If I give V in and if I give any V in, then output will be 1 at all the time. However, if there is a change in input from 0 to 1, what is happening is there is a change in output from 1 to 0. So that is there. Now this transistor has seen a change in its output. So this inverter has seen a change in its input, so it reacted and its output changed from 1 to 0, which means V2's input is changing from 1 to 0. So V2 will go from 0 to 1, but that is the TP LH delay, it is going from low to high. So we are looking at 50% of its input to 50% of its output, that should take 3 time units, right, because that is what the inverter says. Then you look at V3, V3's input is changing from 0 to 1, which means its output should change from 1 to 0, right, but that is the TP HL part of the inverter. So that you will have, and finally V3 is, so V1 settled down already. So you can see that V1 V in settled down already with respect to this XOR gate. V in has already settled down, but there is a change in V3. This change in V3 is going from high to low, right. However, this is going to flip the XOR gate to go from low to high. So, you go and look at low to high of the XOR gate, that is 5 nanoseconds. So, after 5 time units, when after this transition, you will see this transition. If I go and look at what is happening here, this output is supposed to be remaining at 1 through and through. However, because of the change in input, there is some change in all the input waveforms here, which is changing the input waveform at the XOR gate. The XOR gate momentarily goes to 0 and then the output goes back to 1. Logically it should have been at 1 all the time, but it momentarily goes down to 0 and comes back up, and that is about 8 nanoseconds delay. So, it is taking about 8 nanoseconds of time. So, for this 8 nanoseconds, what we have is something called a glitch. The output should have been 1, but it goes momentarily to 0 and then goes back to 1. So, let us see what happens if there is a 1 to 0 transition in V in. A 1 to 0 transition on V in will make V1 rise after 3 time units, V2 to fall after 3 plus 2 equals 5 time units, and V3 to rise after 5 plus 3 equal to 8 time units. So, at time t equal to 8, XOR gate is going to see a change from 0 to 1. This XOR gate is going to see V3 changing from 0 to 1. The XOR gate also sees V in changing from 1 to 0 at time t equal to 4, because that is the TPHL delay. So, that is 4 time units. So, the change in input here has resulted in the change in the output here at the time t equal to 4 itself. However, there is another change that is coming through another path, which also results in the change in the output. So, this time the change is from 0 to 1, and for about 9 time units the output is not in the steady state. The steady state output must have been 1, but the output is not in the steady state. There is a glitch of time period 9 nanoseconds. So, this is a way to analyze combinational circuits. So, remember, this is still a combinational circuit because there is no feedback path. Generally what we do is we determine the worst case propagation delay through these circuits. So, if you look at the previous slide, this circuit can either I can report a delay of 8 nanoseconds or 9 nanoseconds, but I have to say that for 0 to 1 transition and back to, so from 1 to 0 transition and back to 1, it is going to take 8 nanoseconds. However, if the input goes from 1 to 0, the output will go from 0 to 1 back to 1 to 0 and back to 1, and that will take 9 nanoseconds. So, every time I have to report 2 delay values. Typically what we do is we take the worst case delay and report that as the delay of the gate. So, we have a gate here which is of delay 2 nanoseconds, that is the worst case delay whatever it takes. There is some other gate which has delay of 4 nanoseconds, and if I make a circuit which puts these two back to back, I want to find out what is the worst case delay that is happening in the circuit if I put 2 components back to back. And the propagation delay for this one would be any change in input here in the worst case will require 2 time units to come here plus another 4 time units to go here. So, its TP is 2 plus 4 equals 6 nanoseconds here. So, this is slightly straightforward. I take the worst case here, I take the worst case here, I add both of those up, that will give me the worst case here. Let us take this circuit which is slightly more complicated. We have some gate here and another gate here which is feeding another gate here and which is driving one of the outputs. The output of this gate is also directly given to the output of the circuit. So, in terms of the circuit, overall circuit, I have 2 inputs and I have 2 outputs. I want to capture the relationship between these inputs and these outputs. I want to see when these outputs will arrive depending on when the inputs were given, or I want to calculate the time difference. So, let us see what the delays in this circuit are. So, if I change this input here, then it will take 2 time units to come through this plus another 5 time units. So, this red line will change at 7 time units if there is a change in input here, right. So, that is the first path. The second path is this path. in this path, if there is a change in input here, then after 3 plus 5 equals 8 time units, the red line will change. So, the red output, this top output, the one here can change either at 7 time units or at 8 time units, depending on which input changed. If I do not tell you which input changed, if I ask you this question, what is the worst case delay, then we take the worst case path, which is this green path, and we have to report that this output in the worst case will change 8 time units after any of the inputs have changed. In fact, it is only this input change which results in 8 time unit delay. This input is actually slightly faster. However, in the worst case I have to report 8 time units. And there is also this direct path from this line going through this gate to the output, that is the blue line, and this change in input will result in a change in this output. The change in input from of this line will not change the output there. So, it only this input can control this output, so that is 3 time units. So, Tp is maximum of 2 plus 5 because of the yellow path, 3 plus 5 because of the green path, or 3 because of the blue path. So, Tp is 8 gate delays if I treat this whole thing as a black box. If I do not specify various input to output combinations, if I just ask you what the delay of the circuit is, then you have to give me the worst case delay through all the paths for all the outputs with respect to all the inputs. So, this is crucial. If I just ask you for what is the delay of the gate, you have to first of all find out all the input to output paths, and I want just one number, which means you have to take the maximum of all the path delays across all the different gates and whatever their connections are and so on, and you capture the relationship between all outputs to all inputs. So, if I want something specific, then this output line is only 3 units away from this input, and the change in input here will not really change this second output line. However, as a circuit, it takes 8 time units in the worst case, because you do not know what input is going to come. In the worst case, it is going to take 8 time units. Let us do a slightly different circuit. In this case, there are 2 sides. So, this circuit is given here, and there is another circuit. So, let us say there is agent A here and agent B here. Agent A is giving some inputs and transforming it. So, this circuit is transforming A's inputs and giving it as input to B. It is also taking something from B and transferring it back to A. So, that is what this green box, the circuit is doing. If I want to calculate the delay of that, then we already know the delay of this sub circuit. It is 8 time units. However, there is also a path going from this direction to this direction that will have a delay of 9 time units. So, as a circuit, this green box will take maximum of all of those. So, it is maximum of 2 plus 5, 3 plus 5, 3 and 6 plus 3, or 9 gate delays or 9 time units. So, in the worst case, if I ask you what is the delay through this, you have to report that it is 9, because without telling you the inputs and output requirements that I have, if I ask you for the delay of the circuit, it is actually 9 time units. Right? In the worst case, you have to do it for, you have to wait for 9 time units. So, this notion of waiting for 9 time units and so on is necessary. This understanding that it will take so much time is necessary. We will look at the notion of timing analysis in a later video, but as of now, these are combinational circuits. So, if the gates have basic delays, you can calculate the delays of combinational circuits. In reality, gate delays are not so simple. The time delay of a gate is affected by various parameters. So, typically the propagation delay is the intrinsic delay plus some factor due to the load. So, there is every gate has some intrinsic delay, plus depending on what you are connecting to it, it may take some output. So, I can give you a small analogy here. Let us say I am teaching a live classroom, and so there are 2 parts of this preparation for the class. So, I need some amount of time to prepare for the class itself, right, and let us say I give you an assignment, and if there are 10 students, I need to grade 10 homework papers. If there are 100 students, then I have to grade 100 homework papers. The amount of time that I take to prepare for the class is the intrinsic delay, right. Whether I am teaching 10 students or 100 students or 1000 students, I still need to prepare for the class, that is intrinsic delay. And then there is load dependent delay. Depending on the number of students that is there in the class, the amount of time that I will take to in preparation for this course will vary. So Tp equivalently in an electrical circuit, the propagation delay of a gate is there is some intrinsic delay plus something due to the load. Even if the circuit is not loaded, even if it is not connected to anything, there is always some intrinsic delay or some basic delay that the gate will have. So a change in input will take some finite amount of time to change the output. So let us take this slightly complicated example. What we have is, we have various gates here. We have one inverter here, which is gate number 1. We have 2 OR gates which have 3 inputs, 2 OR gates which have 2 inputs, one AND gate with 2 inputs, one AND gate with 3 inputs. So all the gate types are listed here. Let us assume that the input capacitance for each one of these gates are given here. So it is 10 femtofarads, 15 femtofarads and so on. And I also know for each gate there is some intrinsic delay plus some factor into the load that the gate drives. So for NOT gate, let us assume that the intrinsic delay is 0.05 and the load dependent delay is 0.017 into CL. So this is the overall propagation delay of the NOT gate. Similarly, for the 2 input AND gate, there is an intrinsic delay of 0.15 plus output dependent delay of 0.037 times CL and so on. And let us also assume that X is connected to a load which is equivalent of 4 inverters, Z is connected to a load which is equivalent of 4 inverters. Let us assume that this is the basic setup. So each gate has an intrinsic delay and each gate also offers some input capacitance to its driver. So this gate number 2 will offer some capacitance to inputs A and B. The gate number 6 will offer some capacitance to input capacitance to this gate number 2 and gate number 1 and so on. So let us look at the delay through each of these gates. So let us look at T1 first. Once you understand how T1 is worked out, the other things are all straightforward. Let us look at how T1 is worked out. The delay through T1, if I look at gate 1, any change in input C will change in the output here, right. So you look at the output of gate 1, it is connected to gate 6, gate 3 and gate 5, correct. So there are 3 places where the gate is connected and okay. So now let us look at the overall delay. So if I look at delay through the inverter, it is 0.05, that is the intrinsic delay, plus 0.017 into CL or whatever the load capacitance is. What is the load for the inverter? There is a load coming because of this input here. So in fact there are 2 places to which it is connected. So this C bar is connected to 2 inputs of the OR gate, and this is a 3 input OR gate. Let us look at the 3 input OR gate. The 3 input OR gate offers a load of 20 femtofarads to its drivers. So you have 2 into 20 here because of that, and if you go and look at where else it is going to gate number 6 and it is going to gate number 5. So gate number 6 will offer a input load capacitance of 15 femtofarads because OR gate 2 offers 15 femtofarads as input capacitance. Similarly, this OR gate 5, numbered 5, is also a 2 input OR gate that also gives another 15. So 0.05 plus 0.017 into 2 times 15 plus 2 times 20 is 1.24 nanoseconds. So that is the delay of the inverter T1. Let us look at T5 for instance. So if I want to calculate the delay of T5, then T5 is driving only one gate, which is an AND gate. So, let us look at T5, it is a 2 input OR gate. So, 2 input OR gates delay is 0.2 plus 0.019 times its load capacitance. What is the load capacitance? Load capacitance is coming because of 7, and this is a 3 input AND gate. 3 input AND gate offers a capacitance of 20 to its driver. So, you put a 20 here. So, 0.2 plus 0.019 times 20 is 0.58 nanoseconds. So, let us see how T6 and T7 are calculated. So, T6, if you go and look at T6, T6 is a 2 input OR gate. So, 2 input OR gate and it is driving. So, as the assumption says here, it is driving 4 inverters here. Right. So, T6 has 0.2 plus it is going to drive 4 inverters here. So, that is 0.019 times 4 into 10. So, that is 0.96 nanoseconds. Similarly, this AND gate here T7. So, if you go and look at 3 input AND gate, so that has 20. So, it is offering 0.2 plus 0.038 into CL. So, that is 0.2 plus 0.038 into 4 times 10, because that is, we are assuming that there are 4 NOT gates that are connected, and 4 NOT gates give 10 femtofarads as their input capacitance. So, that is 4 into 10, the delay is 1.72. So, again if I break it down, what we did is, every time I wanted to calculate the delay through the gate, I first of all looked at what the gate is and looked up the formula, and once I know the formula, I need the load capacitance though. For the load capacitance, I go and look at where all it is driving. I will pick up those gates and look at their input capacitances. I will add all of that up appropriately, and that is what I did here. This is the delay through each of the circuit components. If I want the delay through the circuit itself, then there are several paths. There is a path from A to X, there are paths from B to X, then there is path from C to Z, D to Z, then there is a path from A to Z, B to Z, and so on. There are several paths that are there. For each of these paths, so if I look at T of A to X, it is going through an AND gate and an OR gate. I look at the delay of the AND gate, it is 0.705, delay of the gate number 6 is 0.96. So, I will add 0.96 and 0.705, that gives me 1.665. If I go and look at B to Z, B to Z goes through gate number 3 and gate number 7. So, I am looking at this here, gate number 3 and gate number 7. Gate number 3 has a delay of 0.78, gate number 7 has a delay of 1.72. I add all of that up, that is 2.5. Let us look at C to Z and D to Z, these are more interesting. If I look at C to Z, there is a path coming from C through 4 to 7 to Z, there is a path coming from C through gate number 3 to 7 to Z. So, there are 2 paths, right. So, if I have 2 paths, I have to look at the maximum of the delays, and that is what this one does. So, if I look at T of C to Z, there is one path going through 4, so it is T4 or T1 plus T maximum of T3 comma T5, right. The reason is it is going through 2 different paths, and finally it is converging at T7. So, what we have is, so let us do this slightly more carefully. If I look at all changes in C will take T7 anyway. So, T7 is added outside, and there are multiple paths to go from C to Z. So, I want the maximum of all those paths, right, all these paths, and to find out maximum of all these paths, I go and look at each one of these paths. C to Z goes through 4, so there is T4 there, then C to Z also goes through T3 comma T5, so I take the maximum of T3 comma T5, but both of them go through the inverter first. So, you look at this input, it goes to T5 and this also goes to T3. So, maximum of T3 comma T5 plus T1 is the delay due to the path going through the inverter. T4 is the path that is going without the inverter, all of them go through T7. So, if that is the expression eventually we get, and if you do the arithmetic it will be 3.74. If you look at T of D to Z, so D has one path going from 4 to 7 and then one path going from 5 to 7, right. So both of them have 7, so you have T7 plus maximum of the delay through T4 or T5. So T4 and T5 I pick up the delays from here 0.78 and 0.58, the maximum of that is 0.78, added to delay of 7 which is 1.72, the summation of that is 2.5. Now if I go and look at all these delays, T of C to Z is 3.74, which is the largest of the delays. So in the worst case, if I do not know anything about when the inputs are coming and so on, it is possible that C comes the last, and because of which Z will change at 3.74 units away from that. So this path where it takes the largest delay is called the critical path. So critical path is C to Z, it is the critical of all of these delays, right. So that takes 3.74 time units. So this is how you analyze the delays of combinational circuits. So what we will do in the next lecture is we will look at some basics of sequential delays. So circuit elements which are sequential elements, we will see how their delays are coming through. But this is a slightly involved example, but I suggest that you go through this to understand what we have done so far. So in this circuit I took the appropriate formula, added the appropriate loads and got the delays for each of those gates. Then I looked at all the paths going from inputs to outputs and I added up all the delays carefully. So I got several path delays, and from the several path delays I picked the path with the largest delay, I call that the critical path. I say that the delay of this whole circuit is now 3.74 nanoseconds. So all these other internal details are now hidden away from you. I will, if I have to sell this circuit to you, I have to say that in the worst case it is going to take 3.74 nanoseconds of delay, and for some input cases it could be faster, but in general I have to tell you that it is going to take 3.74 nanoseconds delay, and that is how I can sell the circuit. I cannot say that the circuit is faster than that. Okay. So I will stop this video at this point and we will resume with sequential elements in the next video. So thank you so much, and I will see you in a little while.